Hello, in this video we are going to look at the velocity selector, specifically from this past year question from May-June 18 paper 42. So open up the question, let us read. Oh, such empty spaces. So explain, I need to write. This explain is normally asking the question how. Okay? A uniform magnetic field and a uniform magnetic field. So we have B and E may be used as a velocity selector for charged particles. So this is to select a particular velocity. Okay, select a particular magnitude of V. Okay, so normally when this kind of question come out, first thing I'll do is I'll scroll, 3 marks. Okay, so there should be at least 3. If you're feeling a bit insecure, 4 points. All right. Number 2, if they give you empty space and then some lines, you have the option of drawing your explanation, but please make sure the diagram you draw is labeled clearly, or writing the explanation, or both, just in case you feel that you are good at one and also good at the other one. All right. So I think the first thing we will draw is, if you watch the video, the whole setup is already there in the video, the lecture video. But let's say you just want to try to see if you can remember or not. And just to change things up a bit, I'm going to draw my plates as vertical. I know in the example video, in the theory video, I explained this with horizontal plates, but mix things up a bit to make sure that our understanding is good. All right, so what we'll do is we'll have some electric field, okay, inside the plate. So I'm just going to label them. So this is the direction of the electric field. The exact polarity really doesn't matter, okay, but if I already label this way, this is positive and this is negative plate lah. Okay, so we must have the particle enter the field. Okay, so let's just think positive. Maybe this is a positive charge, positive Q. Okay, and this particle inside the field. So let me draw the undeviated part. So this is the straight line for the particle. And the particle is going to enter with a velocity of V. Okay, so obviously this particle will experience an attractive force towards the negative plate. This is our Fe. Okay, so to prevent this particle from turning towards the negative plate, I must apply a magnetic force so that the particle will also experience a force to the left. So left force and right force balance out. But where is the direction of B? Time to take out your left hand. Okay, so to use your left hand, first things first, FBI, thumb is your F, so point your thumb to follow the direction of FB. And now I'm just going to look a bit vulgar on the camera, but point your middle finger to follow the direction of this V. Okay, I'm going to take out my middle finger. Ooh, it looks so wrong, so wrong. Okay, so my middle finger has to be pointing upwards this way. While my thumb, this is my thumb, is still pointing same direction as FB, but my middle finger is pointing upward. A lot of people are going to meme me. They're going to, okay, never mind. Why am I giving you ideas? My index or pointing finger is pointing towards the camera. Okay, it's pointing towards the camera. So once again, thumb follow the direction of green arrow, which is magnetic force. Middle finger follow direction of positive charge, which is pointing upwards. Where is this one? Pointing inside. Okay, so our magnetic field is going into the paper. Let's draw some crosses to show that into. So these are all crosses. I'm just going to draw a few to represent enough level. This is B. Okay, so we need to talk about the relationship between E and B. Now E and B is obviously 90 degrees, okay, because one is going into the paper, one is along the plane of the paper. So that will be my first point. I would say that the electric field and magnetic field are at right angles, perpendicular, normal to each other. Means I draw this diagram good enough. I would say it's okay because this particular diagram, if you look at the setup, it's very clear what is B and what is E. Like I got label. Okay, but if during exam you only use pencil to draw, then you make sure your labels are very clear. All right, so second one. So first point, 1 mark. Second mark, the particle will enter the field. Means I don't have to write charge. No need. All these values are arbitrary one. Or all this polarity is arbitrary one. I just put for fun. Okay, but it's correct. So if you make sure you draw, you better draw correct. You draw the wrong field, then it cannot move in a straight line. They may minus 1 mark. All right, so the particle enters both fields at right angles as well. Okay, so enters both fields at an angle, or at right angles, I guess. At right angles to both fields. Means this one also I show in the drawing can? Can. But we haven't answered the question, this one. Select a particular magnitude or a specific magnitude of V. So the final mark is there is no deviation, or the particle will travel in a straight line for particles of a selected velocity. Okay, so you want to make it a bit more explicit also can. What I'll probably do is I will install a slit here, a tiny gap, so that only particles of a certain value of V can pass. So these are slits. Okay, so make sure you label lah. All right, and if let's say you're feeling insecure, you could say for V equal to E over B. So it's either you memorize this, or I guess maybe it's a big ask. So you could say for undeviated particle, Fe is equal to Fb. So again, this one is just to remind you in case you haven't watched that video yet. So this is BQV. Q and Q can cancel. You are left V is equal to E over B. So only values of selected velocity. This selected velocity is V. This selected velocity V will be equal to E over B. It's a bit like if let's say I want a faster particle, then I can increase the electric field, make this E stronger by changing the power supply of the parallel plate, or make the B weaker by decreasing the current that generates the magnetic field. So just in case it wasn't clear, this E and B is easily adjustable one. This E, okay, cannot spell that. Alright, this E can be adjusted using, let's say, the power supply V0. So I'm talking about the setup in case this thing comes out in paper 5. Who knows? This is your V0. Whatever you connect between these two plates, battery, power supply. Okay? How can we adjust B? Well, B can be adjusted. Okay, B can be adjusted by changing the I, the current that causes the magnetic field B. So remember the beginning of the lesson, beginning of the topic, the way we make this magnetic field is by allowing current to flow in a conductor. Okay, so don't forget these are all basic ideas that they can ask. All right, moving on. So all this is just extra because what I can just say in a velocity selector, if I said question, in a velocity selector, the scientists wish to allow a particle of a smaller value of V to pass through the gaps between the slits. Provide a suitable suggestion on how this can happen. Well, if I want a smaller v to pass through the slit or a slower particle to pass through the slit, I can decrease this v naught, decrease E, or I can increase B by increasing the magnetic field. All right, okay, moving on. Part B. Okay, here, this diagram very familiar. Of course lah, I got draw my own diagram one. Particle having mass m and a charge of a positive 1.6 times 10 to the power negative 19 coulomb. Negative 19 coulomb passes through a velocity selector. They enter a region of magnetic field with magnetic flux density 94 millitesla and speed this much, as shown in figure 8.1. Okay, let me just assign some values. This is Q, this is B, and this is V. Okay, and you can see this is the diameter. Diameter is 15 cm. It will rotate inside the magnetic field. Watch the video to figure out why it moves this way. Okay. The direction of uniform magnetic field is into the page and normal to the direction which the particle is moving. Wow, miss, they so nice, huh? They give hint to part A. Yeah lah, if you know what to write in part A lah. So I think to make this better, I will add uniform. Wait, they already mentioned uniform, but in case they didn't, I will add the word uniform in front of electric field, magnetic field. Okay, anyway, back to the question. Particles are moving in a vacuum with a circular arc of diameter 15.0 c. Show that the mass of one of the particle is 20 U. 4 marks. Okay, so we are trying to find m. Now, in case you forget what is U, U is the specific mass. Okay, the unified atomic mass unit. So in case you feel that, how will I know that? Well, you can actually find this in the first page of your exam book or your answer sheet. Okay, so this is called the unified atomic mass unit, and I'm going to paste it here for you. Hopefully my laptop won't hang. If you're wondering why the in-between shots, the edit feels a bit weird, well, it's because my laptop is pretty done with COVID-19. Okay, anyway, rambling over. Here you can see the atomic mass unit is this value. Very nice. Okay, so we are trying to find whether it's 20 U. I guess I'll settle that one later. Let me find what the exact mass is in kg first. So you could say, for these particles, this circular arc means that the magnetic force provides the centripetal force. So magnetic force here will be BQV. Thankfully, everybody is 90 degrees. This is mv squared over r. We can now start simplifying the equation. V and V will cancel out, and I'm finding m, right? So I rearrange. M will be BQR over V. Okay, I can substitute now. Now go back to the question. What is the value of B? B is 94 millitesla. Put inside. 94 times 10 to the power negative 3. Charge is positive 1.6 times 10 to the power negative 19. Okay, 1.6 times 10 to the power negative 19. What is the radius? Diameter is 15. So radius will be 15 divided by 2. 7.5 or 0.075. Have to be in meter because everybody here needs to be in SI. And what is the velocity of the particle? Again, also given. 3.4 times 10 to the power of 4. So I'll put this here. 3.4 times 10 to the power of 4. This is my m. Okay? So always start with this one. And then try to come up, rearrange based on what is needed from the question. Okay, so I'm going to press my calculator now. Okay, from my calculator, it's 3.3176. So 3.32. All right, here lah. M will be equal to 3.32 times 10 to the power of negative 26 kg. All right, so normally I will then copy the value of 1U from the front part of my question paper. 1U is 1.66 times 10 to the power negative 27 kg. So hence, M would be 3.32 times 10 to the power negative 26 divided by 1.66 times 10 to the power negative 27 U. Okay, because this is 1U. So 3.32 is how many U? Okay, let's divide and hope for the best. Negative 27. Okay, I get 19.99, which is approximately 20 U. Proven. Yes. Okay, where are the marks? First mark, magnetic force is equal to centripetal force. Here is 1 mark. Either you write in a sentence, which is always better, or at least you write in an equation. Okay, you rearranging and substituting here is 1 mark. Okay, BQV is mv squared over r is 1 mark. And final answer by division, this step is 1 mark. Which means if you start from here or some other equation that doesn't start from this, you will lose the first 2 marks. So this part is very important. You can be even more explicit lah. Like for example, the centripetal force provided by magnetic force. Okay, so just that sentence will help. All right, part C. On figure 8.1, sketch the path in a uniform magnetic field of a particle of 22U having the same charge and speed as the particle in B. So this 22U is heavier. It's more thick. Okay lah, not thick, not. Don't use thick in the exam. That's not good. Heavier or have more mass. Okay lah, heavier also. Okay lah, let's do the correct scientific term. More mass. More massive. All right, chunkier. It's a chunky boy. All right, so we're gonna put 22U, but you have the same charge and same speed. So I'm gonna steal this equation a bit. Okay, by rearranging this, I will have R is equal to mv over bq. Okay, I rearrange this equation. Get this one. So now I identify my constants. Same charge, same speed. So this one is constant. This one is constant. Uniform magnetic field, same B. This one is also constant. This means from here, you can tell that radius is proportional to the mass. So now if my mass is greater, my radius must be greater. Okay, 来吧. So this one is very nice because it's not like you can turn here also. You turn here is for negative charge but you don't have place to turn also. So this is not the case. You wouldn't do that, would you? So this is for negative charge and So we're going to turn this way. And because it has more mass, it should turn with a semicircle that has a greater diameter. And we're not really measuring because there's no context to measure. So you just draw a semicircle, something, I guess something like this. Okay, I want to comment a little bit about the drawings I tend to see lah. Okay, these are 2 circles, so this one is okay. What I don't want to see is this. I got students that draw like that. Wait Okay, so here are things not to draw. Sometimes people will think, oh, I just need to draw a larger diameter. So what they'll do is they will draw like this. They follow, and then here like that. Okay. In fact, this one looks a bit like this, right? Why is this like this here? What is happening? So if you want to draw a correct diagram, right, the diameter has to start increasing since the beginning. So since the beginning, this one should already increase more and more, and then hit. Okay. am I making any sense? Okay, here a bit cacat. I once again do draw better if I'm drawing it on a physical whiteboard, but I guess this would suffice. Something like this. Okay, so when it's like this, you didn't increase the diameter here. This is wrong. Wrong. Another one that sometimes I see is like this. Me, see, I increased the diameter. I'm like, what is happening? This is not a circle. Also wrong. So this means, right, the diameter has to increase evenly at every single part of the circle. And if you're wondering why, I will draw two circles for you now. Okay, I am not nitpicking. I'm just saying that it should look like this. You see these two circles? They start off with the same common point here. So this common point will be here. Okay, and then when they deviate, the gap between the red line, the red circle, which is the smaller diameter, and the blue line, which is the one with the bigger diameter, the gap between them will increase over time. So until eventually you hit the detector wall, which is roughly on the horizontal plane here. Okay, so you can see the distance between the red line and the blue line will gradually increase. So this one is okay. I need this shape. All right, this one, what is happening? Don't follow halfway and then shoot out. Like the first one I draw, cannot. Don't suddenly increase this way lah. It's also very weird. So any form that doesn't follow this pattern, you may be deducted mark. Because where are the two marks for this? One mark is when you draw a circular part, a semicircle. And the second mark is larger radius. So I will deduct the mark for the semicircle because if you draw it this way, the blue or this, it's not all wrong. If you draw it these two ways, then these are not semicircles. In fact, the red one looks like an ellipse. Okay, so that's it for the question. This one, we look deeply into how to build a velocity selector. Just for fun, I rotated the velocity selector drawing 90 degrees to compared to what you are used to. And then we looked at the velocity selector and see how this allows us to actually measure the mass of a particle. So if you're wondering, Miss, you know in chemistry, they always tell us, this particle got this much mass, that particle got this much mass. How they do? This is one of the methods where we can use to measure the mass of a particle if we know the charge. Okay, and once we put a more massive or a heavier particle, the radius should increase. You either use this relationship or you also can use logic. You're turning something with a bigger mass, and all the other parameters are the same. B, the magnetic field strength, magnetic flux density, B, the charge, the speed, all the same. So if all the parameters are the same, radius is proportional to mass. Larger mass, you turn a corner, you need a larger radius. So the final part I talk about or I emphasize on is sketching. Sorry, one note not loading. Do you have this during exam? You're like, my brain is not loading. Okay, anyway. Then the next part will be to draw the circular pathway. And it's important when drawing the circular pathway to try to maintain the same shape. So don't draw weird things lah. The blue one is very common. Okay, so if you're thinking of drawing that, then no. Try to draw it in such a way where the new part is further and further away from the old part. Even if the radius is smaller, the same thing should apply. Let's say I draw something of a smaller radius. Okay, so you can see even if it's a smaller radius, the distance between the blue and the red line should increase over time. Okay, that's it for the question. Please make sure your shapes are correct and your life is good. If you find this helpful, like, subscribe, share with your friends so everyone can learn physics together, especially if you are learning alone from home. All the best in your studies, and I'll see you in the next one. Bye-bye.